Okay, number 15, they give us a function that's in a table form. Give us some values for t and values for f. And it says we got a closed interval 1 to 15 as the values shown as such, and they define a g function here to be the area from 1 to x of f of t dt. And it says using the intervals 1 to 3, 3 to 6, 6 to 10, 10 to 15. What's the approximation of g of 15 minus g of 1 obtained from the from a left Riemann sum? So bottom line here is remember that if I were to do the integral of f here, I would get g, because again, f's antiderivative is g based on our formula here. And so g of 15 minus g of 1, that's just the integral from 1 to 15 of f. So with that said, we just want to find, all we're really asked here to do is find the area under the curve based on a left Riemann sum. Okay? So we can see that we do not have uniform subintervals here, so we can't just have the length times all the different heights. Okay, so instead, if we go through, and again, if you need to make yourself a picture of this, feel free. You got the point 1, 2, you got the point 3, 3, you got the point 6, 4, you got the point 10, 2, and you got the point 15, negative 1. So if you plot those points, again, even roughly like that, I can get an idea of, again, starting at my left-hand point. My left-hand point I'm going to draw to the right. And then the next one I'm going to draw to the right. Next one I'm going to draw to the right. Next one I'm going to draw to the right. And the last one I'm not going to draw anything. True? We're starting at the left-hand point. So with that said, it's just a matter of figuring out what are the areas of each of these rectangles. Well, this first one goes from 1 to 3, so that would be 2 by, and the height's determined by the first height, which is 2. So that one would be 4. The next one goes from 3 to 6, so that would be 3 by, and the height here is 3, so it would be a 9 there. Next one goes from 6 to 10, that's 4, and its height is determined by the 4, so we get 16 here. And the last one goes from 10 to 15, which is 5, the height is 2, we get 10 here. And if we add those all up, we get 13, and 16 makes 29, plus 10 would be 39. And that corresponds with letter E, as it should. Questions on that one? What else? Mike? 16, they give us, it says the volume of an expanding sphere is increasing at a rate of 12 cubic feet per second. So recognize that that's just a derivative here, which is represented by dv dt. It's got volume compared to time. So again, the giveaway is the units here. Got a volume unit over a time unit. It's dv dt. So we know that. It says when the sphere is when the volume of the sphere is 36 pi cubic feet, how fast in square feet per second is the surface area increasing? All right. So ultimately, we need this dA dt as our unknown here in feet squared per second. Okay. So that's what we're after here. So the question is there a way to relate these two quantities, this volume and this area? And we know that they're both related to r here. True? So if they're both related to r, and again we know that the formulas here are 4/3 pi r cubed, and then the s formula is 4 pi r squared. Alright, so then again the question is how do we relate then? Because if we were to do this integral here, okay, we would get dv dt over here, and we could get something r and then dr dt over here, and if we did that, we get 4 pi r squared dr dt to be exact. Okay, we would know that that's 12. Okay, and it says when the volume is 36 pi, so with that information we could find the r in question, and ultimately we'd find dr dt. True? Because we know that the volume is 4/3 pi r cubed again, and we know if that's 36 pi, we can figure out the radius that would make that true. If we multiply by 3/4 here, obviously dividing by pi, we'll get rid of the pi's. Multiplying by 3/4, we get 27 equals r cubed. So conveniently our r would be 3. And when you get a non-calculator problem, most of the time they're going to give us fairly decent numbers to work with for the time factor. Alright, so with that, we know that the radius at the time in question is 3. So we'd end up with 36 pi on this side. If we divide, we'd get pi over 3. There's our dr dt. 12 and 36. 12 on top, 36 on the bottom. So that would be our dr dt. Now, the question though is not what is dr dt. We're looking for ds dt. I put dA dt first, but it's really S. We'll call it S for surface area. Okay. So bottom line here is if I know dr dt in this problem, though, okay, now can I work with this equation over here and do the same thing and do ds dt and get 8 pi r dr dt? If I differentiate that equation with respect to time, okay, what do I know? I know that r is 3 and I know that dr dt is pi over 3, don't I? So pretty much home free at that point then. 3 here, we got pi over 3 here. 3's we cancel out, we get 8 pi squared. And if you look at the choices, does that appear to be an option? Okay. So there must be something wrong then, or not? Okay. Did I miss a? Oh, you're right. That should be pi here, right? So it should be 1 over 3 pi. So there we go. So 1 over 3 pi, that would cancel the pi's out too, and we simply just get 8 then, because the 3's would cancel out, the pi's would cancel out. Okay. So 8. And that should be A. I believe that's correct, right? Yep. Good. All right. So again, related rates problem. Again, key issue in any related rates problem is to identify the derivatives that they give us and the ones that we're after. Okay? Find an equation that relates the variables, differentiate with respect to time, okay? And then plug in the given information, and we generally will have enough to find the one variable that we need. Okay? In this case, it wasn't direct. We had to find an intermediate derivative first. Okay? But then once we had that intermediate derivative, we could use it in the other equation. We ultimately had to do that differentiation with respect to time twice. Okay. And again, the reason is because could we write a sentence that involved just v and s? You know, and again, the answer to that is yeah, we probably could have here. Okay. Ultimately, we would have had if we could have solved this for r and then plugged it in here. But if we did that, we'd have the square root of s over 4 pi, which ultimately putting that in here and cubing it, that might get pretty messy. Okay. It'd be easier just to keep them separate. Find dr dt and then use it in the other one. Okay. So it could be done. You could write a sentence that was v in terms of s and then differentiate with respect to time, but like I said, the derivative would be much more difficult to deal with. What else through 19? 17? Number 17, they give us that fact that f of x is equal to 15 minus g of x. And we're dealing with negative 2 to 2 as our domain. And it says negative 2 to 2 of the square root, or not square root of, but just f of x minus g of x dx. Right? So we want to know essentially what is the answer to this integral. Well, if we plug in our f of x, we'd have 15 minus g of x minus g of x. True? Alright, again, that is our f function. And if we combine in here, we'd have negative 2 to 2 of 15 minus 2g of x dx. Alright, and you'll notice that in the choices that we have there, they haven't actually come up with an integral answer for the g part here. Okay, this is basically just a properties problem. Okay. What do we know about these two? If we take these two, we could separate them because it's a subtraction. We could do the integral from negative 2 to 2 of 15 minus the integral of, and we could take out a 2 also, 2g of x from negative 2 to 2. Okay. And ultimately, this 15 dx, it's a constant. The antiderivative would be 15x. And so if we did 15x on negative 2 and 2, we'd get 30 minus negative 30 would be 60. Minus 2 times negative 2 to 2 of g of x dx. And that one matches up with e. Questions on number 17? What else? 18. On 18, we have the integral from 4 to, or 2 to 4, that is, of d dt of 3t squared plus 2t minus 1 dt. Alright, so if we're going to differentiate this, okay, which we could certainly do, okay, and then anti-differentiate it, okay, wouldn't we ultimately get back to the argument itself? So when I do the fundamental theorem here, ultimately going to get that, aren't we? Taylor, you're going to see Miss Beacons before you leave today. Don't forget. Very adamant about that. Alright, so ultimately, again, the derivative of this is just going to be, 6t plus 2, but if we anti-differentiate that, we're going to get right back to what we started with. The issue here, though, is becomes with the 3 part right here. Okay. If we were to, I don't know why I got 3. Not 3, how about 1? What about the 1 part here? Because again, if we were to differentiate this, we'd get, again, 6t plus 2. Okay. And then if we anti-differentiate that, would the minus 1 part be here? Because again, if we followed the order of operations here, we would definitely do we'd simplify the argument first here. Okay. And so the question is that negative 1 actually there? No. Okay. So ultimately, if we differentiated this, we'd get 6t plus 2. If we anti-differentiate that, we get 3t squared plus 2t. And then we would evaluate it on 2 and 4. Okay.
And why are you differentiating to begin with?
Well, so it says d dt. Yeah. All right. And so then if we put in our 4 here, we're going to get 16 times 3 would be 48. 48 plus 8 would be 56. And putting a 2 in there, we get 4, should be 12. And 12 plus 4 would be 16. And so we ultimately get 40.
If you do it with the 1 in, you still get 40. Is that
Why would that be? Why would it not matter if we kept the 1 in there or not? All right. Yeah, we're ultimately going to have 56 minus 1, and then 16 minus 1. And we go minus 1, what's going to happen with the 1s, whether we kept it there or not? And just cancel out anyway. Remember, the key with the fundamental theorem here is when we integrate here, we need an antiderivative. Okay, does it matter which antiderivative? No, we could have anything here. We could have plus 1, minus 3,000, and we'd still get, guess what? We'd still get 40. Okay. So in the scheme of things, it really doesn't matter. We don't need it there. If we had it there, it's not going to make it wrong, because ultimately we'd still get 40 either way. What else? Questions on this one? Next. And number 19, they give us this is the rate of change of the velocity of a particle moving on the x-axis is given by the function r of t equals negative sine t minus radical 3 cosine t for t greater than or equal to 0. And at t equals 0, the velocity is 1. Okay. So ultimately then, keep in mind that they told us that this is the rate of change of the velocity. So this is really what? What is the rate of change of the velocity? It's acceleration. Okay. So this is just an acceleration function that they gave us. Okay. And so let's see if we can figure out what's going on here with the choices here. So it says that as t begins to increase from t equals 0, okay, which statement is true? So in other words, as time starts to pass here, time 1, time 2, time 3, and so on, okay, which of these statements is true? So let's start with part A here. It says the particle is moving to the left and its speed is increasing. Okay? So the particle is moving to the left and the speed is increasing. All right. So again, keeping in mind that we know that that time 0, the velocity is 1, which would indicate that it's actually moving to the what? Time 0, it's moving to the right. Okay. And again, as it begins to, as time begins to increase from time 0, the like I said, the velocity at time 0 is 1, and we know that velocity being positive means that it's moving to the right at time 0. Okay. So at time 0, it's moving to the right. All right. So knowing that, the A and C are essentially out at this point. Okay, and then if we look at the choices on B, C, and D, the difference is that that B says the speed is increasing, and C says that the speed is decreasing, and E says that it has a constant speed. Okay? Now, knowing that when we have an acceleration equation that is variable here, we should expect that the speed is not going to be constant, I would venture to guess. So it's probably either going to be increasing or decreasing. So let's take a look at what is the acceleration like. Okay. Well, let's start with what is the acceleration at 0? Well, the acceleration here, sine of 0 is 0, and then we're going to get negative 3, radical 3, and then the cosine of 0 is 1. So our acceleration at 0 would be negative 3. True? Okay. So let's think about what that would indicate then for this particular situation. Drawing a picture of this, we know at time 0, I'm going to draw a velocity graph, so let's draw our velocity versus time graph here, and think about which one of these is the right answer. So again, we know that the velocity at 0 is 1, so here we are with velocity, it would be at 1, okay, and then at this same time, at time 0, our acceleration is negative radical 3, so at that point, our slope would be a negative something, right? Okay, and just for argument's sake, if we did say time, or if we did A at pi over 2, for argument's sake, we'd get sine would be 1, so we'd have negative 1 minus radical 3 times cosine of pi over 2. We know cosine of pi over 2 is 0, so we get negative 1. So even over here at time pi over 2, the acceleration is still negative, which means the slope of the velocity curve would still be negative. It's a little less negative because negative 1 is less than negative 3. Okay. All right, so ultimately, again, this is our velocity curve, if you will. This is a picture of the situation. Okay, we know that the velocity is positive, okay, and we know that it's decreasing. Okay. And so, bottom line here is if that's our curve, if we have a velocity that's positive, okay, and decreasing, okay, if we did the absolute value of that, which is the speed, okay, what would that do to our curve? Anything? Wouldn't it be the same curve? Okay. And so since velocity is decreasing, then what could be said about the speed? The speed is also decreasing. So therefore it should be choice D. Alright. Had the velocity been negative 1 and the speed, say, was increasing, if we did the absolute value of that, okay, or the velocity was increasing, just say it had been something like that instead. So if the velocity would have been negative 1, let's say for argument's sake, and the acceleration positive, okay, then the speed in this case, the flip of that would have been this graph, and it still would have been speed decreasing, wouldn't it? Okay. All right. So again, based on that information, the velocity being 1, we know the value of the velocity, we know the slope of the velocity, okay? And so again, since it's positive valued and it's got a negative slope, okay, that means that our speed and the velocity graph are going to be the same graph in this case. Okay? Absolute value would keep that the same. Okay? All right. So therefore, it should be D. So moving right and speed decreasing. All right, next part, 20 through 24. Right. And number 20, we've got some choices to make here. It says f is a differentiable function on the open interval a to b. If f has a relative minimum at c, and c is between a and b, which of the following must be true? So it must be true. We have that the fact that the derivative at c has to equal 0. Okay? So ultimately, again, we have a minimum point. We know that. Okay? It's given information that we have a minimum point. So if we have a minimum point, okay, question is, does the derivative have to equal 0? Okay, and the answer normally would be not necessarily, but they told us this is a differentiable function. Because remember, we could have a minimum at a point like that, couldn't we? Okay. But then would this be a differentiable function?
No.
No. So really, since it's a differentiable function, does the derivative have to equal 0?
Yes.
At a minimum? Yes. Okay, so 1 is n. Okay. All right, and let's look at number 2. That the second derivative, okay, must exist. Okay, so second derivative must exist. So the question is that true? And must the second derivative exist if we have a minimum? And if not, if we don't think it does have to exist, then is there a picture that we could draw such that we would have a minimum and the second derivative didn't exist? If we're going to say that that's false, then we should be able to provide a counterexample, true? Let's come back to that one in a minute. It says that in number 3, it says that if the second derivative at c exists, then the second derivative is greater than 0. Okay? So think about that one. That's indicating that if second derivative value, okay, then the second derivative equals 0, or excuse me, is greater than 0. Okay? And if it was greater than 0, what would that indicate for our function? That it would be concave what? It would be concave up at that point, okay, which ultimately concave up at c. Okay? So our normal picture would just be that then. True? Okay? So we'd say at this point c, okay, we know we have a minimum. Okay? It's a differentiable function. Okay? We know that we have a relative minimum at this point. Okay? And ultimately, again, we know that out of our choices here, the only time that we can have a minimum is either at an endpoint or a stationary point or a singular point. Okay, singular points are out because that would be where the derivative doesn't exist, and that's not going to be possible here if it's a differentiable function. Okay, so the only possible choice here to have a minimum would be that the derivative equals 0, okay, which keeps 1 in the mix. Right? All right, and then the other two, again, keeping in mind that also I didn't mention the endpoints here. The endpoints don't come into play because they told us that c is between a and b. Okay? So it can't be at an endpoint here either. So our only choice is that we're somewhere in the interval between a and b. Okay? And again, it is a minimum, so that means that the only choice is that the first derivative has to equal 0. Okay? All right. So getting back to this business about the second derivative. Okay? If we look at our second derivative, again, we know that in choice 3 that it says that if the second derivative exists, then the second derivative has to be greater than 0. Okay? So the question is, would there be a way to draw this minimum so that it would not be concave up? Ultimately, if we're going to rule that out, okay, we got to be able to find a way to draw this so that it wouldn't be concave up. Okay? So would there be a way to have a minimum and have it not be concave up? Okay. And the only problem with the corner, though, is that it says it's differentiable. True? So if it's differentiable, then corner is not an option, is it? Okay. All right. So, like I said, the question is then, is there a way that we could draw that such that this would make number 3 false, that the second derivative exists, and that it's not concave up? Connor, you got an idea?
Well, if it's a quadratic function, then the second derivative would be 0, and it says that it has to be greater than 0.
So ultimately we have f of x, to say we have f of x equals x squared, we could very well have that as our function here and have a minimum at 0. True? And the derivative of that, of course, would be 2x, and the second derivative then would be 2. Okay. So ultimately the second derivative here would be positive, wouldn't it? And so that would actually, that particular example would kind of verify that that would be true. Mike, take a sentence.
It's not relative minimum at 0.
What is not?
It's that function at 0 is not the relative minimum.
For this function?
Yes.
At 0, this one would have a relative minimum.
No, it's not. You can draw it. It's like this. And
X squared?
It's like U.
X squared is a parabola.
No, no.
You're talking about this particular example that we're talking about?
Never heard the same also.
Remember, this is f of x equals x squared.
Okay, now.
If it was x cubed, it would look like this. I agree. Right?
Is it a linear function, like
Constant.
second derivative with the 0 limit?
So the issue, though, if it were linear, okay,
Yeah.
the issue would there be a way to have a minimum somewhere in that interval?
If it was cubed,
Okay. If it was cubed, would it have a minimum there, though?
then, but it was quadratic,
Yeah.
it's different.
And again, if we have some crazy piecewise thing, it would have to be differentiable too, though, wouldn't it? Okay. So of the functions that we know, there doesn't appear to be any that would make sense here, would it? That would make those two things not work. Okay. So it would seem that that the second derivative should exist here if we have a minimum. Okay. We can't seem to find a counterexample, can we? Okay, I mean, I guess the first one, go back to number 2 here, that the fact that the second derivative exists. Right? And I guess the question is, would there be a function that would have a minimum, okay, where the second derivative wouldn't exist? And the answer seems to be what? Seems to be no. I mean, again, just if I had this general picture, whether it came from a quadratic or some other function, okay, if I again have the derivative equaling 0 here, okay, and it being a minimum, there appears to be concave down in this area, which would indicate that the second derivative should exist. Otherwise, it wouldn't be any concavity at all. Okay. All right.
But the answer is only 1.
And is it really?
Yeah.
Oh, that's not good. I wonder if could be a possible typo. Okay. Let me check on that one. Because I can't think of a counterexample myself. I would think it should be E, which means all 3 are good to go. Okay. All right. So I'll put some more thought into that to see if I can think of a different counterexample, but I can't think of one off the top of my head at this point. So I'll check that. And if you had, how many of you had choice E on that? Okay. So I'll relook at that and you might get another point for that. Okay, how about next? Up through 24? Okay.
21?
And 21 says a solid has a circular base of radius 3. Every plane cross section perpendicular to the x-axis is an equilateral triangle, and its volume is what? So we got a solid, it's got a circular base, radius 3. Okay. So if it's radius 3, we draw it in our coordinate plane, and we draw our slice perpendicular to the x-axis, and it comes out of the paper at us as an equilateral triangle, as such. Okay. Then our key issue here is, can we write a formula then for the area of that triangle, when we know in general that it's 1/2 times base times height? True? Okay. And we also know that for that that base, if we were to take this and draw it in 2 dimensions, okay, this being the bottom, if you will, we know that that is going to be the distance from here to here, and that distance from there to there is going to be the 2 functions added together, the top function and the bottom function, if you will. And since we have a circle here that has a radius of 3, it would be 9 as our circle equation, so it would be ultimately plus and minus the square root of 9 minus x squared. Okay. So that would be our base, and ultimately we'd have actually 2 of those, so the 2 and the half would cancel out. We just get simply 9 minus x squared for our 1/2 b part. So 1/2 b would be that, because again it's 2 times square root of 9 minus x squared would be the distance from here to here, length of the base. Alright, now the other question is, can we find an expression for the height here? Okay. Well, knowing that this is an equilateral triangle, and knowing that each of these are 9 minus x squared, square root, okay, and knowing that this is a 60 and this is a 30, and we want the height of this, remember we're in a 30, 60, 90 triangle, is short side is this, the long side, which is our height in this question, is radical 3 times that. So that right there would be our height. So ultimately be radical 27 minus 3x squared. Alright. So ultimately that would be our expression for the area of said triangle. Right? Okay. So let's see what happens if we I would suggest putting these together, because ultimately if we're going to integrate this on negative 3 to 3 here, it's going to have to be a little nicer argument than that. So hopefully if we do our 27 times 9, it's going to be 243. And then we're going to have minus 27.
Wait, why is the base only 1 over square root of 9 minus x squared?
Well, the actual base of the triangle is 2 of those. Okay. But if we split it in half, it's going to be 1 each on each side. Alright, so if we do the multiplication here, we got minus 27 here, would be negative 54x squared. And then those two together would be plus 3x, not x squared, sorry, it's 54x. No, that is right. That is squared, and this is to the 4th. Alright, and if we factor out a 3, we're going to get x squared minus 18x, x to the 4th, that is, 18x squared, and 3 into that would be 81. Alright, and if we try to factor this, we're going to get x squared and x squared, minus 9 minus 9. And how conveniently that works out, because what's x squared minus 9 all squared, and if we take the square root of that, what's going to happen to this piece? If I have x squared minus 9 squared, that's going to come out, isn't it? Right?
When you had like the base times had originally like the square root of 3 and square root of 9 minus x squared, if you didn't like originally multiply those two together, you had just like the 2 square root.
Yeah, that's true. We could have just done that instead in the first place, right? And either way, it comes out as x squared minus 9 times the square root of 3, if you will. As the x squared minus 9 is squared, it can come out of the radical.
Wait, why are you taking the square root of that?
Because that's ultimately comes from this. These two multiplied together. So this was all under a square root the whole entire time. Alright, so again, that piece will come out nicely. Right.
How did it change from 9 minus x squared to x squared minus 9?
Ultimately, when I did,
Yes.
I just distributed the stuff here. When I FOILed these two, it becomes a plus. And then when I factored it back, the leading coefficient's positive. Alright, so ultimately this right here would be our formula, if you will, for the area of this particular shape. True? And we want negative 3 to 3 of that to sum up the areas of all the slices that we have. So I would factor out the radical 3 first. Okay. And then if we anti-differentiate, we get x cubed over 3 minus 9x on negative 3 to 3. And if we put a 3 in there, we're going to get 27 over 3, which is 9, minus 27. So putting a 3 in here, 27 over 3 is 9, minus 9 times 3, that's 27. And then putting a negative 3 in there, we get negative 9. And we get plus 27 here. And if we go 9 here, minus minus gives us plus, that'd be 18. Negative 27 minus 27 would be negative 54. It shouldn't be negative though, I'm missing something here. Plus, yeah. Shouldn't be getting a negative answer on this. Let's see. We're getting the right answer, but we're getting a negative here, so somehow we're missing a negative on one of these things. See it, Josh?
How did the 9 minus
Yeah,
x
that's what I
squared
was-
become x squared minus 9?
Yeah.
Let's see.
Because you have the radical 9 minus x squared times the radical 9 minus x squared, which should just be
So
9
this was
minus x
343, right? Back up here.
Yeah.
Minus 27, minus 27. And these two are plus 3x to the 4th. And if I factor out 3 out of that, I'm going to get that and that. And that. Yeah, why can't that change? Because ultimately I'm foiling this. I got 243, minus 27, minus 27. And then these two are plus 3x to the 4th, right? So if I have that, then there's no reason I can't rearrange the order and make it 3x to the 4th minus 54x plus 243. And if we factor 3 out of that, we get this. And that factors to x squared minus 9. Think of what can go wrong with that to get from here. Because if it was 9 minus x squared, obviously we'd have the opposite of this. We'd have 54 minus 18, which would be 36 that we're after. Yeah, why? I'm trying to think what mathematically would not be okay with doing that. I guess if we I guess the probably easier thing here would be is if we didn't multiply this in there, if we just kept it separate, then we would have gotten ultimately back up here in this point we would have had 9 minus x squared times radical 3 times 9 minus x squared. Had we done it like that, then our radical 3 would have been paired up with just 9 minus x squared. Then we wouldn't even have got to this point. I guess one of the things that happens generally when we deal with quadratics and quartics, anything with an even power like that, is that when we do that, when we work with those, remember keep in mind there's always plus and minus answers when we deal with such equations, right? So if we essentially reverse it and have x squared minus 9 instead of 9 minus x squared, okay, that could give us a reverse answer of what we're after. Okay? We're ultimately getting the same answer. I mean, the way we did it, we'd have that, which we know that can't possibly be negative. Okay? Ultimately, in a sense, we've just differentiated or anti-differentiated the other way, going 3 to negative 3, if you will. Either way, is it still the actual area of the or the volume of the shape that we're getting? Okay? We just know the volume can't be negative, so we do get the right answer here. We just got to make sure that we're careful and make it positive. Notice there are no negative answers on that anyway. But had we done it this way in the first place, then we wouldn't have had to mess with all that. Okay. So if we anti-differentiate this, we're going to get 9x minus x cubed over 3, which ultimately is going to give us the 54 minus 18, which would be positive of what we're looking for. Okay. So I guess if you did try it this way, just recognize that when you deal with cubics and, or not cubics, but quartics and quadratics, okay, there's a possibility that we might get a negative instead of a positive. Okay. If we change the subtraction, if you will. Okay. So, like I said, I guess best bet would probably be just to recognize that you already had 2 of the same things here, so multiplying that out is not really going to do you any good. So, yeah, I guess what it stems from here, I guess mathematically, is this. When we did this step right here, when we factored it into x squared minus 9, okay, we ultimately, to get back to this, we could do this times this, okay, or we could do negative this times negative this and still get back to the same thing. Would that be true to say? Okay. This times this gives us this, that's true. But wouldn't negative this times negative this give us also positive this? Okay. There's the problem right there mathematically, is that step. Okay. Because remember, negative this is 9 minus x squared, isn't it? So either one of those two factors would have worked. The fact that we reversed it gave us a negative answer, but bottom line, still the same effect. We still get the right answer, but it's just negative. Alright, what next?
Wait, how like do you make yourself fast enough to do that this like
I would probably, it would be obviously much faster to do it if you did it this version, because then you don't have to multiply all that out. So, I mean, again, you recognize that this is a problem that's going to take some time, so when are you going to do it? Last. Okay. Any problem that's going to take you a while, I wouldn't do it right away. Okay. Don't spend 5 whole minutes on this problem and then not have it down for some easier problem. Okay. I'd rather get this one wrong than get 3 easy ones wrong. True? So, like I said, do all the ones that you can do quickly first. Anything that you know you're going to have to think about for a while, or anything that you know is going to take some time, okay, skip it. Alright. What else? Mike?
I have a common example about time taking.
Oh, you found one?
So, yeah.
Come back in number 20. What'd you find?
It's x raised to the 3 halves.
So if you do x to the 3 halves, you got the derivative is 3 halves x to the 1 half, right? So ultimately this would equal 0 at 0. So, and it also equals 0 here, right? And keep in mind that if we did our number line here at 0, if we did left of that, if we do left of 0 here, are we going to get? If we do left of 0 here, though, we're going to get a negative under a radical.
Instead of starting with this, and so the relative minimum is one side.
Let's take a look.
Just like doesn't have a differentiable relative minimum.
Yeah, I mean, obviously a 0 can go in there, and 0 is going to give us 0 for the derivative here. But again, there is no left side of the function. And that the c value here has to be between these two. It says c is between a and b, so it's got to be on some open interval. I mean, I agree that the second derivative wouldn't exist here because we'd have when we do the second derivative here, we'd have x to the negative 1 half, which would be 1 over, and that means if we put a 0 in there, we'd have 1 over 0, which means that wouldn't be okay. So I agree with that part. The only thing I'm struggling with here is the fact that it says that c has to be between a and b, which,
There'd be no a, just the left of it.
right, there would be no a, I guess. There would be no left endpoint here. I mean, it would be the left endpoint, if you will. So I'm not sure if that qualifies. I'll think about it a little bit more, though. Alright, let's carry on here so we can get the rest of them answered here. We got, what else up through 28? 22 says the derivative of y equals f of x. Y of 2 is equal to 4. Then y of x is equal to following. Ultimately, again, we know that dy dx here is equal to some function. They don't tell us what the function is this time, but this would be one of our typical problems where we wouldn't be able to find the antiderivative because we don't even know what f of x is. So if we went from 2 to t of f of t dt, and we added a 4 on the end, wouldn't that be an expression that gives us our antiderivative of y? And ultimately that matches up with, I guess that would be B, right? Actually, I'll make that an X. 2X. Next.
24.
On 24, it says we got the graph of a e to the x plus b over e to the x plus 1. Graph has horizontal asymptotes at 3 and negative 5. We want to know what is the value of a plus b. Okay. So if this is going to have asymptotes at 3 going to the right, that means the limit as x approaches infinity here of a e to the x plus b over e to the x plus 1, that's going to have to equal 3. So that would have to be a true sentence here, wouldn't it? As x approaches infinity, my function would have to approach 3 in order to have a horizontal asymptote on the right-hand side. Okay. So the key issue then is what's the a going to have to be in order to make that happen? Yeah, it would have to be 3, because ultimately if I had 3 e to the x over e to the x, that would be 3 at infinity. E to the x and e to the x are behaving the same way. And the b here, no matter what I add or subtract here, is going to be relevant at infinity. True? Okay. So therefore, a would have to be 3 here in order to make that true. And then ultimately, in order to find the value of a plus b, we would need to know the b value, of course. We have the a value already. And if we look at our if we go to negative infinity here, we know that a e to the x, well, we know that has to be a 3, so we can just use 3 if we want to. Or we can leave it as a either way. We know that this has to equal negative 5, because as we approach negative infinity, the y values go to negative 5. Okay. Now remember, what's going to happen here when we go to negative infinity? These two are going to become what? Well, either way, at a negative infinity, they're the same, aren't they? So if these are the same at negative infinity, okay, they're the same except for this one is 3. Okay. And remember these. If I just take a look at just the top only, if you will, okay. If I look at just the top only at this point, as this goes to negative infinity, this e to the negative x, e to the negative 2 million is going to be really close to what? 0. So ultimately this is 0, and this is b, right? So this limit in general is going to be b over, and this same effect here, this is going to be b over 1, isn't it? In order for that to equal negative 5, what does b have to equal? B would have to be negative 5, wouldn't it? And so if we take our 2a and b and we add them together, we got a 3 and a negative 5, we get the answer of negative 2. What else? Mike?
I have another example.
Alright. Let's see if we have others here, and then we'll go back to that one. So hold on to it for a second. What else? Up to 28? Josh?
You say 23.
23, we just need the derivative of the inverse sign. So in general, the derivative of the inverse sign is going to be 1 over the square root of 1 minus u squared times du dx. So in our case, we're going to have square root of 1 minus 3x over 4, all squared, and then times 3/4, the derivative of u. And if we simplify, we're going to get square root of 1 minus 9x over 16, 9x squared, times 3/4. And the issue here is that we have a fraction here on the bottom of our fraction. We can remedy that by multiplying, by essentially putting these two together. So if we made this 16 minus 9x squared over 16 on the bottom, we could take the 16 out. We got a common denominator with these two. We could take the 16 out now because it's on the bottom. It's in the division. We can take it out. So we'd be left with 1 over, and then we'd have 16 minus 9x squared here, and we'd have that come out as a quarter. So remember, it's going to come out on the bottom of the bottom, if you will. So if that 1 wasn't there, it would just be on the bottom. And then remember, we still have 3/4 here. So we got 3 on top. The 4 and the 1/4 will cancel out. We'll get 16 minus 9x squared here. Should correspond to one of ours, should be letter E. Josh?
25.
On 25, it says that the slope of the curve dy dx then is 2y over x, and it says that if at each point x, y on a certain curve the slope of the curve is 2y over x, then the curve is a what? Ultimately, if we want to get back to what curve this came from, if we separate variables here, we could go 1 over 2y dy equals 1 over x dx. So if we multiply by dx and then we divide by 2y, we have such. If we do natural log of absolute value of 2y, natural log of x plus c. And if we compose both sides with our e function, we'd have 2y here, and we'd have e to the ln x plus c. And ultimately, if we change that to e to the ln x, e to the c, e to the c, remember, is just a constant. E to the ln x is just x. So we'd have cx, 2y. So y would be cx over 2, which ultimately is something x. So therefore, should be our just end up getting squared somewhere. They have it should be a parabola. Let me take a look at my work on that one. We'll finish that one up tomorrow. So tomorrow we'll start with we'll finish up with everything else up to 28, including that one, and then Mike will give us his example. Unless I find another one too.